Dr. Greek is president and co-founder, Americans for Medical Advancement, an organization that advocates for science-based medical research. Ray is co-author of the books Animal Models in Light of Evolution and Frequently Asked Questions about the Use of Animals in Science. Welcome to the program, Ray.
Oh, well, thank you for having me, Lori.
Ray, briefly summarize the paper concerning the experimental mouse model.
Well, the journal the paper was published in is called Plough's Medicine, and as you stated, it is a very prestigious journal. And the article discusses a drug called fialurdine, or it's usually abbreviated FIAU. And in 1993, this drug was given to some people to treat hepatitis B. And when it was being tested in phase 2 human clinical trials, 7 out of 15 people that were given the drug developed acute liver failure. And as you stated, 5 of these people died and 2 more required a liver transplant. So this was an extremely bad outcome for a drug. And the National Academy of Sciences recently did a retrospective analysis of FIAU. And they said that there was absolutely no animal data at the time that could have prevented this. And this is what led these authors, these scientists, to try and come up with a mouse model that would, in fact, have prevented the death and the liver failure.
So tell us, what issues do you take with its protocol or the author's comments?
Well, the protocol was fine. I mean, this is just a regular mouse study. They tried to invent a new mouse, which they did. Their mouse model is called the TK-NOG mouse, and it's a knockout mouse. It's a genetically modified mouse. This mouse is actually a chimera, meaning that it has some human genes in it, and they claim that their mouse has 90% of a human liver. In other words, the liver that the mouse has is 90% human and 10% mouse. And the issue that I have with their concept, not so much as their protocol, is simply the assumption that they make. And the assumption that they make is if they can make a mouse liver that is human enough, then this new mouse will work well when it comes to testing drugs for the potential to induce liver failure. And in fact, their mouse did succeed in mimicking the response of humans to FIAU. FIAU did cause liver failure in this particular mouse. And so they go on to say that this is going to revolutionize, drug testing, and they now have a predictive model for liver failure and so on and so on. And that simply doesn't hold water. You can have a mouse that's 100% like a human liver, but the rest of the genes are still mouse genes, and therefore the liver is going to react like a mouse liver, not necessarily like a human liver. It may have reacted like a human liver in this one case of FIAU toxicity, but that doesn't mean that it has any predictive value for any other drugs. In other words, what they did was reverse engineer a mouse so that it would react like a human in this one case. And that's actually not that hard to do. What is difficult to do is to then engineer a mouse that reacts like humans prospectively. In other words, if you give some human, say, 19 or 20 drugs, and, let's say that the human reacts however the human reacts, in order for the mouse to have predictive value, the mouse has to react the same way 90, 95, 98% of the time. And that just has never happened. And it never will happen because we understand the differences between mice and humans, namely that mice evolved to be mice and humans evolved to be humans. And they're very, very different despite having very similar genetics.
Ray, in the study, the implication is that you need live mice to host the humanized liver in order to do the toxicity study. Is that correct?
That's more or less the assumption, yes. Because we can't do this on humans, we need animals to be human surrogates. And the problem with the assumption is that animals and humans evolved to be what they are. Mice evolved to be mice, humans evolved to be humans. And even if we had 100% similarity of genes, that does not mean that our outcomes to drugs and disease are going to be similar. For example, we know that humans respond differently to drugs. For example, in the study that was done in 1993, 8 out of the 15 people tolerated the drug very well. They did not die from liver disease. They did not need a liver transplant. 7 out of the 15, 5 died, 2 needed a liver transplant. So when you have human variability like this, it's kind of nonsensical to say, well, we need a mouse to predict what humans are going to do. Which humans are we talking about? Because most of the humans in the study did fine with the drug, whereas a minority of the humans, died or needed a liver transplant from the drug. And that's the problem in a nutshell. If we got rid of every single drug that's on the market today that caused a really bad side effect in somebody, some human, we wouldn't have any drugs. Every single drug on the market today will kill someone if it's given to the right person in the right dose.
Yeah.
So the point is that this new mouse liver, this new mouse model is being hyped way beyond the science that actually supports it. And this is a common theme in animal experimentation because a lot of people make a lot of money off this. But the press release and the actual PLOS medicine article really go way beyond what the science supports.
Well, thank you for explaining that so well. Ray, there's another very new study you pointed out to me, you also wanted to critique, is one having to do with cleft palates in dogs and the purported relationship to cleft palates in people. Please tell us about that article and what you feel its problems are.
Yeah, the second news item is similar to the first in what it mistakenly assumes. The second news item concerns a breed of dog that was recently discovered at the vet school at UC Davis, and this dog suffers from cleft palate. Now, a news release about this discovery stated that the scientists responsible for this discovery had said that, quote, they hoped the discovery, which provides the first dog model for the craniofacial defect, will lead to a better understanding of cleft palate in humans, end quote. And this article was also published in the PLOS series, in this case, PLOS Genetics. Now, the notion that genes do the same thing in all species is simply false. That notion is refuted by the reality of everyday life. The fact is that animals and humans are very complex systems, and this means that a gene that causes one thing in an animal may cause something totally different in a human, and vice versa. And an example of that would be the birth defects that occur in humans called phenylketonuria, that's one birth defect, and another birth defect is called Sanfilippo syndrome. We know which genes cause these birth defects in humans, and these genes are normal variants in monkeys. In other words, monkeys have these genes, and they do no harm, and they probably help the monkey do whatever it is those genes help the monkey do. In other words, they're beneficial to the monkey, but they're harmful to the humans. Now, this alone invalidates the concept that once you know what a gene does in a mouse or a monkey or a dog, you automatically know what that gene does in a human. Okay? So these genes cause no harm to monkeys, but they do cause harm to humans. And as I described earlier, the same is true for metabolizing drugs. Even different humans metabolize drugs differently. In the FIAU case, some of the humans metabolized a drug to a toxic substance that killed their liver, whereas other humans metabolized the drug to a substance that was completely harmless to them. So very, very small differences between species, and indeed very, very small differences between humans, can result in the same drug being harmful to one and beneficial to the other. And this holds true for genes and pretty much everything else in the human body. Another example of this would be the fact that humans and mice both have the gene that in mice allows them to grow a tail. Humans have the exact same gene. The reason that we don't grow a tail is because that gene is turned off during our embryogenesis or during our fetal development. So even when two species do have the same gene and it does the same thing, that does not mean that they're going to look alike or act alike or respond to drugs and disease the same way.
Ray, let's go back to progress in testing for potential drug toxicity in humans. What will we do if we don't use animals?
Well, that's a very good question, Lori. The fact of the matter is that what we have to do in order to learn whether a drug is going to adversely affect you is basically test the drug on you. And we don't have to literally give you the drug, but what we should do is expose your genes to the drug, and that is happening every day. We do not know what every single gene in the human body does, but we do know what some of the genes do. And so what we can do is we can put the gene in a little well, and then we can drop a little bit of the medication into that well, and we can see whether it turns that gene on or off. So if we're trying to turn a cancer gene off, we want to see whether the drug, in fact, does that in this little computer assay. And if we want to make sure that a side effect gene does not get turned on, we can also see what happens to your gene in that little well. And that little well is on a computer chip, and then you put the computer chip into the computer, and the computer says whether any of these 20,000 genes were turned on or turned off or remain neutral or whatever. Now that is not only Star Trek medicine, but that's actually happening today, okay? And just as we saw in that FIAU study, half the patients responded one way, half the patients got liver failure from the drug.
Right.
So that's what we want to know. We want to know which half are you in? Are you in the half that does well with the drug? Am I in the half that does well with the drug? Every one of your listeners wants to know if he or she is going to be adversely affected by the drug. And you're not going to learn that from animal testing. You have to actually test the drug on the human in question or the genes from the human in question. And that is being done. It just needs to be done more frequently. And the way that it can be done more frequently is if society funds human-based research so that we figure out what all these genes that we have do and what the differences are between the people who responded poorly to a drug and the people who responded well to a drug. That is the way to have side effect-free medicine.
Ray, how strong is the desire of journal reviewers and editors, as well as research grant agencies, to see protocols that include animal models?
They have a very strong desire to see those protocols, in part because their jobs depend on it. What you have to remember is that these journal editors and even the referees in the journals, for the most part, work for academia. And any human-based research grant that comes from NIH really doesn't help the university. The university does not profit from that grant, whereas any animal-based research grant that comes from NIH, the university will receive between a third and a half or maybe even more of the money that comes from the NIH. So if somebody has $1 million grant, as much as 500,000 of that might go directly to the university. It won't be used in the research. It will just be free money for the university. And the university can then take that money and do anything they want to do with it. They can pay the salary of the basketball coach. They can, add a wing on to the administration building. They can do anything they want. And but some of these large universities will get upwards of $100 million a year of that kind of money free from the people who do animal-based research. These same people are the referees of the journals, the editors of the journals, and so on and so on. Matter of fact, a study was done not that long ago that showed that research grants for doing human-based research received much lower scores at NIH than did animal-based research grants. So the whole system is tilted. The odds of you getting a grant if you do human-based research are not good, whereas the odds of you getting a research grant if you do animal-based research are in fact very good. And this just carries over into all aspects of the biomedical process, the scientific research. So these people do have a vested interest in it in more ways than one.
Ray, are there any advances in toxicity testing and other areas of medical research that don't use animals?
Yes, there's actually been a lot of advances. Most of the advances have been around the use of computers and around the use of computers with in vitro technology. But, we don't really need a lot of advances in computer-based technology or in vitro technology. A lot of what we have right now is adequate. The problem really is that we continue to use animal models even though we know the animal models don't work. What we should be doing is either human-based research in the form of clinical research, epidemiology, genetics, genome-wide association studies, things like that, and then combining that with our new in vitro methods and our new computer methods. One thing that you hear a lot about in the news is an organ on a chip. And probably someday that will come to fruition. But again, it raises the question of, well, which organ or whose organ? Because the organ, your liver, is going to respond differently than my liver. So all of these new advances need to focus on human-based research, and specifically on the human that is you and the human that is me. We have to personalize this. One size does not fit all. We have to figure out what the drug will do to you as opposed to what the drug will do to me. Now, that's the future of medicine, and a lot of work is being done on that. Again, these genetic studies, these genome-wide association studies, even epidemiology studies are now including a genetic arm in the study. So that is all really, really great news, but still we have to stop the animal testing, which doesn't work in the first place.